I'd like to explain a little bit of how the oscillator is creating these types of results. Okay, suppose that when we turn on the radio, we create a transient response. This C and L resonant circuit, because we've created a very high resistance through this path back to ground with the tapped L equivalent circuit, has a very high Q. So if you do have a transient response, you're going to ring at the frequency of the resonant LC combination, and that was with the values here about 1.08 megahertz. So go along into steady state, and then at time t0, which I marked in blue, and let me just use a blue thing here, the current in this coil was a negative number. It was minus 1.71 milliamps if you read it off, or if you read it off the curve. I've defined the currents such that they're on this side are coming in this direction, going into the dot and then coming out the other side. And the same true is for this one, and the same is true for this one. So the current in this direction is negative, so what I really have is a positive current this way of 1.71 milliamps. Likewise, the current in this direction is negative, and it turns out to be 1.45 milliamps. That means that there's some current going down in here of the difference of the two, which is about 0.26 milliamps. That's exactly what I measure. Now, where does that current go? Well, the current comes down here, and it goes back in the resistor. Can't go back up into the transistor. And indeed, the current in this resistor is exactly the same value. Now, if you look at the transistor current, it's equal to 0. And the reason for that is a couple things. One is the current that flowed down in here created a drop across this resistor to be a little bit higher than the voltage needed to turn this junction on. We're estimating that this node voltage would be around 0.88 when we bias this transistor on. That current is actually lifting this point up just slightly, enough to turn off this transistor. Because when current is coming out of these dots, then current will be coming into this dot on the transformer. So it wants to turn the transistor on, but that current is holding it off. So this part of the transformer isn't doing anything for that instant in time. All right, let me erase these now and take a look at the next instant of time, which I labeled T1, but I did that in red, so let me mark this down in red here. At that instant in time, the current in the coil L4 is again negative, but it's around 0.88 milliamps. And the current in L5 is also negative, and it's equal to 0.88 milliamps. That leaves 0 left over here. So nothing comes into this resistor from the capacitor. Now, with current going out of the dot in both these coils, it's trying to have current come into the dot on the coil on top, just like before. But now we've taken that level off of this resistor, R33, and current begins to flow down this path. The value is about 0.11 milliamps. So now I've established a current down this path. The transistor amplifier is now going from cutoff to actually the active region. Now let's take a look at what happens. Let me erase this. At the next instant in time, I called T2. And I mark that with a purple dot. So let me go back and grab that. At that instant in time, the current in L4 is actually equal to 0. And the current in L5 is equal to a minus 1.46. In other words, it's going in this direction. The current in the capacitor, again, I just read these off of the simulation, going in this direction of 1.46 milliamps. And the current that's flowing in L6, which is also the collector, is about 1.58 milliamps. And then the current that's down in this resistor is about 0.1 milliamps. So what happened as this current started to increase, and the reason that was happening is because we had currents in both these coils wanting to start to get this current to flow, and that current flowing provided the current for this resistor, and the excess started to come back up here. Eventually, enough comes back here to shut off the current here. And so you can see what's happening in this particular part of it. So the transistor got turned on, more current started to flow, and that current came up back into here. So once the oscillation started, it kind of increased itself at that particular instant in time. Okay, now as time begins to increase, because current is coming out of this dot, it wants to come into here and get larger. So it wants to increase this number. The current that goes down in here, fairly constant, and so the excess comes back here. Some of it starts to split off back this way and then back this way. And so we'll begin to see then a decrease in the current that's here. And that's going to be my next point. I'll call that T3, which was the black dot. Let me just erase this again and write down what happened next. I'll use a black notation here. So at time T3, the current in this coil is a positive value, which means it's flowing in this direction of 1.75 milliamps. And the current in this coil is flowing in this direction, just the opposite now, of 2.02 milliamps. And the current in the capacitor is flowing in this direction because you've got some extra current left over, and it's around 0.26 milliamps again. And then most of that, well, that's all going down into here. And that's, again, causing this current in here to go to zero. Now, part of the reason for that is that with current going in this direction, it wants current to come out of the coil on this side, on the dotted side. And of course, current can't flow in that direction, so the transistor gets shut off. So what happened initially was we had current flowing in this direction. Some had gone back down in here, and that kind of held off the transistor. But because current was flowing in this direction, it wanted to pull current in here, and eventually did. The excess current came back up here, and eventually forced this current to now change directions. And then when that's happening, this is going to change directions and begin to decrease this current, which eventually will shut off the transistor. We're kind of back to where we started from. Now all of this is happening relative to the tuned circuit on this side. So we're creating a lot of harmonics, but the only signal that comes through from this side is a single 1.08 megahertz signal. Take a look at that in the simulation. And that's how the oscillator perpetuates itself. If you were to change any of these dots, the oscillator would actually die out. So the dot notation here was important because of how it works to maintain this feedback loop. It starts to go unstable, but eventually shuts itself off. So what we're going to get is a series of pulses in Q7, the frequency of which is related to the tuning of this coil. So take a look at page 26. Now, some of the things that we've already mentioned. So the oscillation is occurring from the transformer T5 with the variable capacitances that are there. We saw that the average value of the waveforms was 0. That's because an inductor is a short circuit for DC. There's also a phase change with the voltage across the resistor R33 because of how the dot notation is. And then we saw the transistor being turned on and turned off, but it's done in a frequency that matches the resonant frequency of the primary side of T5. So what you have now is a current that's flowing into the collector of transistor 7 that has an average value and then an AC component of 1.08 megahertz. So effectively GM is changing, has a constant part to it and then a part that's changing. Now GM is going to multiply V pi of transistor 7, and that's going to be my received signal. What I'm going to do shortly is increase the received signal, but if it was 624 kilohertz, then the multiplication of that with the 1.08 megahertz signal would create a sum of frequencies and a difference of frequencies, and that would, one of which is 456 kilohertz. And that's going to pass through our transformer T6, which is going to be tuned to that frequency. This is node voltage 41. This is the collector voltage to ground of transistor Q7. You can see there's a lot of distortion here. So there's a lot of components in frequency, but the period roughly is about 455 kilohertz. This is the output of the transformer on the secondary side. And you can see a very clean signal here, and the frequency, this is exactly 455 kilohertz. Now we could also turn PSpice into a spectrum analyzer by changing the x-axis from time to frequency, and it shows us here the frequency components that are in node voltage 41. You can see the 455 kilohertz signal. Now that's coming from the fact that we're going to multiply GM times VPi. VPi has a 624 kilohertz signal, and that's going to multiply the 1.08 megahertz variation of GM. That's going to create our multiplying circuit. It's going to create two frequencies, 1.705 megahertz and 455. But the tuned circuit, which is transformer T6, and again this is the output of T6, is only going to let through the 455 kilohertz signal. And so that's what we're going to hear in our radio. Also look at the current in the collector of transistor Q7 now that I've got a carrier voltage of 0.1 volt. You can see now the currents are going up and down, so we've got more frequency components here. But again, the period of this is the reciprocal, which is 1.08 megahertz. So I did also the spectrum analyzer, and you can see these four frequencies again. The received signal around 624, the oscillator of 1.08 megahertz, the product of those two creating these two frequencies. But even with all this stuff here, the tuned circuit's only going to let this one through. And that's how the oscillator works. There's a feedback path that once the oscillator gets started, it maintains itself and eventually shuts off the transistor and then turns it back on again. So a very non-linear oscillation. And again, you wouldn't see this by just looking at the voltages in the circuit. They appear to be all sinusoidal, but the currents that are going on in this transistor circuit are pulse waveforms, but they have these specific frequencies. This takes us then to our lab experiment. Concepts that we've covered are AM, the super heterodyne receiver, the AM detector and automatic gain control, the IF transformers, and of course the IF amplifiers, and then the AM oscillator and mixer. Techniques we'll learn in lab are how to use the function generator to create an AM signal. We're going to do some troubleshooting by taking some DC measurements with a digital voltmeter, so that we can see whether we've made a wiring mistake or a soldering mistake. We're going to measure gain, bandwidth, and Q with our scope. And lastly, we're going to do tuning, which is tuning the IF transformers to 455 kilohertz. And this is the AM portion of our radio.